Welcome back, dear students, for again our chapter chemistry of the inner transition elements. Now so far we have completed the many properties, electronic configuration. In that we are seeing the two type of the configuration. One is the ideal configuration, second is the observed configuration. So based upon the configuration, we are seeing the many properties. So electronic configuration of the two types. One is the ideal and second is the observed or actual, you can say. And based upon that we are seeing the oxidation state. Then we have studied the magnetic property, then we have studied the very important part, lanthanide contraction. And based upon the lanthanide contraction, we are seeing what are the consequences of the lanthanide contraction. After that we have studied the spectral properties. In spectral properties, first we have seen the color of the lanthanides, and then we have studied the absorption spectrum. So based upon the electronic configuration, we are seeing these properties. Now the last property that is left is the ability to form the complexes that we are going to cover in today's lecture. So next important property is ability to form the complexes. That means complex formation tendency of the lanthanides we have to go to study. So before starting this actual part, I will ask one question, that ability to form the complexes is depend upon the which factor? Can anybody have the idea which ion, which element can form the most stable complexes, and if it form the stable complexes, why it will form the stable complexes, not other can form the stable complexes. So ability to form the complexes is depend upon the charge density. One of the important factor. So what is the charge density? You can tell what is the charge density, how it is calculated. So charge density means it is the ratio of charge to the radius. It is charge to the radius. That is the factor where we can calculate the charge density. Now if you compare for the lanthanides ion, then in the lanthanide, what is the charge, how much maximum charge is there? Most of the lanthanides are stable in a 3+ state, common oxidation state. The +3 charge is possible. While the cerium is the only element which can have the 4+ state, or praseodymium, neodymium, or leftmost element like the cell which is half filled, it can form the complexes after gadolinium elements. So maximum charge in case of the suppose lanthanide is the +4 of cerium, or +3 to take. And suppose the radius is very small, we have seen in lanthanide contraction that ionic cell brigade decreases from lanthanum to lutetium. So at different lanthanides have very marginal decrease in the ionic radius, but overall decrease is significant. not much that difference is there, 0.01 like that, 0.02 like that. Difference is there. Or nanometer is the 0.002 like that, nanometer difference is there, 0.001, 0.009 nanometer. So if we take cerium, then we have the charge is suppose plus 3, 1.02 is the ionic radius for the cerium, or plus 3 upon 0.102 nanometer. Calculate this product. How much is there? In case of the lanthanides, the charge to radius ratio is found to be this, or suppose this. Here if we take the point, radius will be again slightly shorter than this when cerium form the plus 4. On the other hand, in case of the transition elements, if we take, one of the important property of the transition elements is they have the multiple or variable oxidation state. They can show many oxidation states. They can show plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7 also. So SC, TI, V, CR, Ma, Fe, CO, Ni, Cu, Zn. This is the first transition series. So starting from this, scandium plus 3, titanium plus 4, plus 5, plus 6, plus 7. So manganese can show the maximum size is plus 7 charge. And if we take the radius of the manganese in lanthanide contraction, we have seen that is the plus 7, Mn plus 7 is 0.46 Armstrong. Then if you calculate the charge density here in case of the trans element as an example, then plus 7 upon 0.46. Now compare this ratio and this ratio and this ratio. If you compare, then which will be higher, plus 7 upon 0.46 or plus 3 upon 0.102 or plus 4 upon 102. So calculate it. So definitely the answer will be this. So charge radius, charge to radius ratio, that is charge density in case of the trans element is higher. While in case of the lanthanide, it is comparatively lower than the trans elements. The 4f electrons which are responsible for the properties are deep inside of this lanthanides, and that's why they are well protected by the outer lying layers. They are well shielded by the outer lying layers, by the IF, ID like that orbitals. That is why these electrons are not easily available for the bonding. While trans element, the electrons which are present, that is outer electrons, and they are well not protected by the other layers. They are well available to the environmental factors when they can come closer, and they can take the parts in the bonding. That is why lanthanides have a weaker tendency or poor tendency to form the stable complexes as compared to the transition element, because lanthanides have the low charge to radius ratio, that is low charge density as compared to transition elements. And that is the reason that lanthanides can form limited number of the stable complexes. They does not have the more stable complexes like the others. Now just I have told, in case of the lanthanides, the characteristic electrons which are present in lanthanides, these are the inner electrons, and these electrons are well protected by the outer lying layers. environmental factors or the surrounding ligand does not easily available these electrons for the body. That means there is a hardly any interaction taking place by the inner electrons and the outer surrounding ligand field. Due to this, what happened? Due to this, the ligand field stabilization energy. Due to this, ligand field stabilization energy in this case of the lanthanides is minimum. Why? Because there is no interaction taking place between the ligands and the electrons present in the 4 orbitals of the lanthanides. On the other hand, if you take the transition elements, the transition elements have the electrons which are outer electron, they can get affected by the surrounding ligands when they come contact. And that electrons, which are the d electron and -1 d electron in transition metal ion, they can be easily available. They can be easily available for the ligand. The ligand can take part in bonding with the inner and the outer and -1 d electrons. And that is why in case of the transition metal ion, the ligand field stabilization energy is higher. While in lanthanide, ligand field stabilization energy is minimum. Now the force of attraction between the these F electrons or the metal ions and the surrounding ligand field is purely electrostatic in the nature. The force of attraction between the metal ions and the surrounding ligand field in transition element is purely electrostatic in the nature. That is why here these electrons, ligand field stabilization energy is here found to be minimum. The attraction becomes weak because that electrons are not easily available for the bonding. But if this ligand contains strongly electronegative donor atoms like chloride or the oxygen atom, chlorine or the oxygen atoms, then if this ligand contains chlorine and the oxygen, which are the strongly electronegative donor atom, then what happens? The force of the attraction between the ligand and this lanthanide ion can become the increases. That is, electrostatic force of the attraction can be increases, and due to this, what happens? The ligand field stabilization energy, which was minimum, which was now increases because of the factor. And as the ligand field stabilization energy increases, definitely the lanthanide have the tendency to form the stable complexes is increases. What this indicates? The lanthanide can form the stable complexes under 3 conditions, we can see, which so stable complexes are formed by lanthanides when number 1, the ligand contains more electronegative donor atoms like chlorine, oxygen, etc. Then ligand is polydentate. And third factor is ligand can form chelates. So if these 3 factors are satisfied these conditions by the lanthanide can form the more stable complexes. Now ligand, what is first tell me what is the ligand? We can pronunciation also as the ligand. So what is the ligand? You have studied all this coordination chemistry in secondary basic, okay, all the basic concepts we have covered in details. So ligands are the negative ions, you can see, or the ions or the molecules which contain the lone pair of electrons. That means they are the electron donors. Ligands are the electron donors. So ligands are the, we can say, the ions or the molecules which are attached to the central metal atom in a coordination sphere in a complex compound is called the ligand. Now ligand is a polydentate. Now ligands of the hot type. Come you see the basic part here now. Very important. So what knowledge we have that can come in picture. Now ligands are the two types. So one is the monodentate ligand and second is the polydentate ligand. So how we define the term monodentate? What is the monodentate? Mono means unique, that is one. So the ligands which can have only one point of attachment, or the ligands which can link or attach to the donor atom, the same donor atom in only one point or the one site, that is called the monodentate ligand. For example, ammonia is there. Ammonia, if you take ammonia, has only one donor atom which contains the lone pair, that is nitrogen. So here nitrogen can be only the one donor atom which can attach to the any metal center at the one point. That's why ammonia is the monodentate ligand. In the same manner, it is the water molecule H2O. Then water also has the only one point of attachment because oxygen is the only one donor atom is there that can be bind or attached to the link to the central metal atom, only one side. That is why it is called the monodentate ligand. And what is the polydentate ligand? The ligands which can have the more than one point of attachment, then that is called as the polydentate ligands. If it has the 2 point of attachment, then it is called the bidentate ligand. If it has 3 point of attachment, tridentate, 4 point tetradentate, like that and so on. So that indicates that the ligands which can have the more than 2 point of attachment. For example, it is the ethylene diamide. The ethylene diamine, then we have the ethylene diamine, 2 nitrogen atoms are there, CH2, NH2, CH2, NH2. So here 2 nitrogen atoms are there which can bind to the central metal atom or link here and form the covalent bond. The arrowhead shows the covalent bond is there. Electrons from the nitrogen will donate to the metal atom. So 2 point of attachments are there. The ligand can bind or link to the 2 different sites, we can say. That is called the 2 nitrogen atom, we call the bidentate ligand. In the same manner, if we take the ethylene diamide, for example of the ethylene diamide. Then we have the CH2NH, CH2. NH. CH2, CH2. And here you have the NH2, NH2. So this is the ER, so it is the diene we can see. Diethylene triamine. Diethylene triamine. And you have the 3 point of attachment for the 2 nitrogen, 3 nitrogen. So it is called the tridentate. If we take the triene, triethylene tetramine, triethylene tetramine. Then here we have the triethylene tetramine of the 4 point of attachment, the tetrahedral ligand. Now, what is the nature of the EDTA? So ligands which are the polydentate. Can so now what is the nature of the EDTA? Let's start with the question. Anybody has the answer? It is the monodentate or the polydentate. If it is polydentate, then what is bidentate, tridentate, tetradentate? What is the nature? So ethylene EDTA, that is ethylene diamine tetraacetic acid. Tetraacetic acid, EDTA. To take, then it has the how many point of attachment? 6. CH2, 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 and here CH2, COO, CH2, COO, CH2, COO, and CH2, CO. So here nitrogen atoms are there. Nitrogen atoms can go to the electron pair here. How many nitrogen atoms are there? Now see 1, 2 nitrogen atoms are there. And here we have the 4 oxygen. Here if we add the H here, H if we added here, then that becomes the acetic acid. It becomes the acid. Ethylene diamine tetraacetic acid. Now here and further. So 1, 2, 3, 4 and 2 nitrogen here. So we have the 6 point of attachment. That's why it is hexadentate, which I said. Denticity is a hexa. The 6 point of attachment further, the metal can be attached here. That is why here the EDTA can form the most stable complex. If we compare the ammonia and the ethylene diamine, then which can form the most stable complex? Say, tell me. The ethylene diamine. So third condition, ligand can form the chelates. When the ligand can form the chelates, what is the chelates first? Tell me, what is the chelates? So chelates are the heterocyclic ring compounds which are formed by the one or more donor atoms. And that chelates, the process of the forming the chelates is called the chelation. And the ligand which can form the chelates is called the chelating ligands here. So those ligands which can form the chelate, those which can form the heterocyclic ring, that is the chelates, and that can form the most stable compound. So ammonia is the more dentate ligand, it does not form any chelates. Here only one point of attachment. Ethylene diamine can form the chelate, just I have told. And suppose this is the copper is there, and this is NH2CH2, NH2CH2. NH2CH2, NH2CH2. So this is the chelate formed by the copper here. These are all the covalent bonds. So ring compounds are there. Some can form 5-member ring, some can form 6-member ring, some can form 4-member ring, like that. So ligands which can form the 6 or the 5-member rings are the form chelates are most stable. So ligand is a polydentate, so EDTA can form the stable chelate. EDTA, oxalic acid, phytic acid, acetylacetone, benzalacetone, these are some examples which can form the chelates. So under these conditions, we can say that these ligand can form, the lanthanides can form the stable complexes. These 3 conditions are there. The ligand contains highly electric donor atom, oxygen, chlorine. Ligand is the polydentate and ligand can form the chelate rings. So, as the 4 electrons are not easily available, the lanthanides does not form any pi type complexes with unsaturated hydrocarbons. And this is not available, pi type bond is not possible. So, like the olefins, in olefins, we cannot have this pi type of the bonding because 4 electrons are not available for the bonding, and that's why lanthanide does not form the pi type complex. So these ions can be easily hydrated in the solution and form the hydrated ions. So what type of the situations are there when lanthanide can form the complex F? So species are there. What are the species can form the complex F? That is the next part. The first one is ion pair association, ion pair formation. So ion pair formation can be possible, and if ion pair is there, then lanthanide can form the stable complex. So what type of complex is generally formed here? So here the by means of the ion pair. Ion pair means for the oppositely charged ion, positive, negative. Suppose any cell is there, so any other plus charge, share minus. So this is the ion pair, and they are attracted by means of the strongly electrostatic force of the attraction. So here it can form the Ln 2 plus by this complex F, or Ln SO4 plus, or Ln CTO4 plus auxiliary ions. So this type of complex F can be formed by means of the ion pair association in lanthanides. Then second is the non-chelated species. Second category of the lanthanides which can form the complex F is the non-chelated. Just we have to mention what is the chelate. If that ligand does not form the chelate, then it is called the non-chelated species. So example in the category, the ligand can like the ammonia or amines. They can form this type of the complex by means of the formation of the adduct. So adduct in the same additional compound. Here we can say the LNI3 or XNH3, like that. This type of complex can be formed. LNCl3, XNH2, like that. So lanthanide can form the complex F, stable complex F by means of the non-chelated species formation, like the adduct by means of the ammonia. All of you know ammonia is the more dented ligand, so it forms the complex F, it is less stable. So second criteria, non-chelated species. Then third factor is the chelated species. So third is the chelated. In chelated species, the first part is non-ionic again. So non-ionic species can be formed here by through means of the chelated species formation, which is non-ionic. So here the example of the category which can form the stable complexes, one is the acetyl acetone. Acetyl acetone and benzyl acetone. Acetyl acetone and the benzyl acetone can form this type of the complexes. So they can form the type LNA minus. So complexes formed by this is LNA minus XH2. So here A dash A indicate the bidentate ligand. So ligand is the bidentate here, and that is mostly the acetyl acetone or benzyl acetone. So this complex is formed which are coming in this non-ionic category. So this is the non-ionic category. Then in chelated species, the next category is ionic species. So B part, the three, we have the B part, ionic species. In ionic species, which can form the chelate. Just we are going to mention the example of the ammonia, the ethylene diamine, diene, diethylene triamine, triethylene tetramine, like that, EDT. Then they can form the chelates which are in ionic species. So non-ionic in the same way only neutral molecules are there like that. No in ionic form, ionic charge is there. Lanthanide can form the complexes, all the lanthanide can form the stable complexes with EDTA. So now the charge is there, it is coming the ionic category, ionic species. It's chelated but ionic species. Then C6H5 O7. Citric acid. So citric acid, ethylene, these are all can form the stable complexes. So this is coming in ionic way, and this is the most stable complexes because they can form the chelates, which are very difficult to rupture. So lanthanide ion can form the stable complexes here by means 3 ways. Now, if you see the color of the lanthanide complexes here, then what is the color of the lanthanide in the previous lecture we are seeing? The color depends on which factor and how they are the color. In lanthanides, the color depends upon that it cannot be changed by changing the anions. The color of the lanthanides cannot be changed by adding color complexing groups also. That is why here the 4f electrons, when the factor is written or the part coming, perhaps student can bore this by understanding same concept. But the very important part that you have to keep in mind, this is the important fact, the 4f electrons which are present or responsible for these colors, these are well deep inside the atom and they are well protected by the outer line 5f and the 5d orbitals, and that's why these 4f electrons are not come in contact with the surrounding ligand field produced by the ligands, and that's why no bonding taking place. There is hardly any interaction of the 4f electrons and the surrounding ligands, and that is why the color of the lanthanide complex, the color of the lanthanide from the complex shape, which form the complex, the color of the complex shape is not affected by any bonded group. Not affected by any bonded group, that indicate that the color of the lanthanides are because of its only the parent metal ion. Parent metal ion, that is the cations here. Only the cation, color of the cation. Other cannot be changed. That is very important part. So lanthanide ion can form now between the mono and the monodental ligand and the bidental ligand. Like ammonia is there and ethylene diamine is there. Among that, which can form the most stable complexes? Ammonia or the ethylene diamine. So ethylene diamine can form the stable complex because they can form the chelates here. With a bidental ligand, 2 point of attachment is there, 1 point of attachment. If you compare the ethylene diamine and the diene, which can form the stable complex or diene. Why? Because it has a 3 point of attachment. So diethylene triamine form the most stable than the ethylene. If you compare the diene and the triene, diethylene triamine and the triethylene tetramine, then we can have this complex. The triene can form the most stable complex because 4 point of attachment. And if you compare the triene and the EDTA, then definitely the answer should be the EDTA because of Hugel intelligence. And that's why most of the practice we are carrying out is with the EDTA. The reason is that it is Hugel intent. So it can replace one ligand by the other 6 ligand, replacement by the 6 points. That means one ligand can be replaced by the other 6 ligands here in EDT. And that is why it can form the most stable complex. So if you see the example of the categories of calcium hexahydrate here, and if you add the EDTA here, then that EDTA can replace how many? 6 replace the 6 water molecules here. So 6 water molecules are replaced by the 1 EDTA molecule. Let us see how much stability there the EDTA. And that is why here the EDTA can form the most stable complexes That's why they are easily hydrated in a solution, and that's why these ions can be recovered in a solution only when they can form the chelates. Otherwise, it's difficult to isolate from the solution. So, ions which are hydrated in solution, aqueous solution, they can be recovered by means of the chelate formation, stable complexes, and that can be stability more. In addition to that, the number of rings are there, stability depend upon also the number of rings in the atom. Suppose if you take the ammonia molecules, NH2 thrice, then how many rings are there in ammonia? There are only no rings are there in ammonia. Ammonia does not have any ring because it does not form the chelates. But if you take the ethylene diamine, then how many rings are there in ethylene diamine? We have seen here NH2, CH2, NH2, CH2, NH2, CH2, again NH2, CH2. So, 2 rings are there. So, number of rings are formed by the 2. If you take the diene, again you have the 3 point of attachment. If you take the triene, 4 point of attachment, you have the EDTA, 6 point of attachment. That number of rings will be more. So as the number of rings will be increases here, stability also increases. So the complexes which more number of the rings are more stable than the complexes which are less number of the rings. This is also one of the important factor in case of the lanthanides to form the ability to form the complexes. Now, if you now go to stereochemistry of the lanthanides here, then the stereochemistry of lanthanides is flexible. So, lanthanide can form the stable complexes ranging from the quantity number 3 to the quantity number 12. So, again, if electrons are easily available, they are deeply protected, they are well shielded by the outer line layer, electrons are not easily available to form the bond. So, the example from the category that in a common coordination number here, that is 3 to 8 or 3 to 6, that the common coordination number where lanthanide can form the stable complexes. So, we have taken the example of the iridium. Iridium NCF6. 3 minus. So what is the quantity number in this complex? What is the quantity number here? First tell me what is the quantity number definition. Then we can come to that point. If you do not know what is quantity number, you cannot able. But if you have studied in previous year in detail. So can anybody tell me what is the quantity number? The quantity number is defined as it is the number of ions or the neutral molecules which are directly attached to the central metal atom in the coordination sphere beyond the number possible based upon the oxidation state. That is called the coordination number of that particular bond. Or we have seen number of ions and the neutral molecule, that is nothing but the ligands. So straight away the number of ligands which are directly attached to the central metal atom in the coordination sphere, that is called the coordination number. Now here, what is the coordination number here in this case? Coordination number is here, number of ligands are attached at the 6 here. So that's why the coordination number will be the 6 in this complex. So what is the geometry as per the coordination number 6 here? The geometry will be the octahedral as per the normal. So iridium complex, erbium complex of the thiocyanide ion, isothiocyanide ion can give the octahedral geometry. If you replace the iridium by the cerium here, suppose the 3 plus state again. What is the coordination number here? Again 6 proton ligands are there, that's why the coordination number is 6 in this case also. So coordination number is the 6 here. What is the geometry expected here in this case of the complex again? The geometry is octahedral. So coordination number 6 indicates that the geometry is octahedral. Suppose I have taken the lanthanum ion AC3 and H2O2. Then what is the Cornelison number here in the lanthanide? What is the Cornelison number in this case? Can anybody tell? So 5. Okay. Anybody answer? Any other answer other than 5? 3 or 2. So all are the wrong answers. So Cornelison number just are told, that is the number of ligands which are directly attached to the central metal atom in the Cornelison pair as per the definition. The 3 plus 2, that is 5, is correct as per the U. But here you have to state the nature of the ligand here. Here ligand is an acetone. The bidental ligands are there. So 2 bidental ligands are there, and we have the 3 molecules are there. So 2 into 3, that is 6, and then 2 automolecules are there. That's why the Cornelison number here in this complex of the lanthanum is 8. And the Cornelison number is 8. What is geometry here? Geometry is square antiprism. Then take the example of the neodymium aqua complex. So NDH2O9. 9 molecules are there of water. Any molecules. So neodymium complex. What is the Cornelison number here in this complex? Can anybody tell? So Cornelison number is very simple, because 9 water molecules are there and water is the monoid ligand. So you have the 9 Cornelison number. So what is the geometry here for the 9 Cornelison number? That is tricapsular. Distorted trigonal prism. The geometry. So neodymium complex, the Cornelison number 9 is tricapsular distorted trigonal prism. So Cornelison number 3 to 6 or 3 to 9 is as per the normal trends in the lanthanides. To have the higher Cornelison number, you have to involvement of the D and the F orbital is required, then only higher Cornelison number can be expected. So we have again take the lanthanum NO3 twice and dipyrite. NO3 thrice, dipyrite. So what is the Cornelison number here in this case? So NO3 3. So NO3 is the bidental ligand here. And that's why 3 are there. So 3 into 2. Again you see that 3 plus 2 means 5 will be the Cornelison number as per your definition. But Cornelison number is based upon the nature of the ligand. So nitrate ions have the 3 into 2 6, and dipyrite are the bidental ligands. So dipyrite is 2 into 2. So 6 plus 4, that is 10. So Cornelison number is 10 in this case. And that is why here the geometry is here in case of the Cornelison number 10 is the bicapsular dodecahedron. Bicapsular dodecahedron, that is the geometry. Now if you take the cerium here, cerium complex of CNO3 5, 2 marks. And what is here the Cornelison number here? The Cornelison number will be again NO3 will be the bidental ligand. So Cornelison number is 10. So again the geometry is same, bicapsular dodecahedron. And if you replace the nitrate ions by one more nitrate ion here, CNO3 6, 3 marks. What is the Cornelison number? Not to the bidental ligand, so 6 into 2, 12. Higher Cornelison number again expected here. There is a distorted geometry will be distorted icosahedron. So this is the stereochemistry of the lanthanum complexes. Lanthanum can form the many complexes, stable complexes, which are stable ranging from Cornelison number 3 to the 12 also. So this completes our the first part, that is based upon the electronic. We have completed the 2 parts now. First of all, we have seen the 2 different series of the inner transition elements, and then what are their position in the periodic table, what are their names, symbol, etc. And then second part, we have studied the electronic configuration of these lanthanides. There are two types are there. One is the idealized electronic configuration, second is the observed or actual configuration. And based upon that, we have seen this property. Which property? The first one, oxidation state. Then we have studied the Maddy properties. Then we have studied the lanthanum contraction, very important part. And based upon that, consequences of the lanthanum contraction. After that, we have studied the spectral properties. In spectral property, we have seen the color and then absorption spectra. And lastly, today, we have completed the ability to form the complex shapes of the lanthanide. So this covers the entire properties of the based upon the electronic configuration. Now next part we are going to study